Dear students, let's start with the fifth part of DCET 2021 question paper. So let's start with the questions of the part 5. So we'll go to the first question, question number 81. The two different types of breakdown in diodes are. So options are Zener and avalanche. Option B is photovoltaic and ionic breakdown. Option C is avalanche and Zener breakdown. Option D is hot carrier and Zener breakdown. Now here, the two breakdowns seen in diodes are Zener breakdown and avalanche breakdown. Okay, so in these options, option A will be the right answer, Zener and avalanche. Now this is a answer because breakdown word is used in the question itself. Otherwise, logically, option C also is the answer because in option C also avalanche and Zener breakdown is given. Okay, so here, if the breakdown word is considered in the question itself, then option A, that is Zener and avalanche, will be the right answer. So the two different types of breakdown in diodes are Zener and avalanche. And logically, if you speak, then option C also can be considered as answer because in option C also it is avalanche and Zener breakdown. Okay. So here, option A will be the correct answer. The two different types of breakdown in diodes are Zener and avalanche. Okay. Then the avalanche breakdown and Zener breakdown are two different mechanisms by which a PN junction breaks. The Zener and avalanche breakdown both occur in diode under reverse bias condition. The avalanche breakdown occurs because of the ionization of electrons and hole pairs, whereas the Zener breakdown occurs because of the heavy doping. Then you can see here, if you see the graphs of both Zener breakdown and avalanche breakdown, so here you can see in reverse bias condition, this is reverse bias condition. So here when the reverse voltage is applied to the diode, the reverse current is going to flow. And there you can see the minority current here. This is the minority current, this is leakage current, and it will be less initially. But as you increase the voltage, it will go till the breakdown voltage. So here in the first case, you see avalanche breakdown happening, and the avalanche breakdown is shown like this. In the second case, you see this breakdown happening here. So this is your Zener breakdown, VZ Zener breakdown. It is happening a little early because of the electric potential of the depletion layer in Zener because it is heavily doped. And here you can see this is a sharp breakdown. This is a sharp breakdown at a particular voltage. So there is a sharp breakdown here, and that is a Zener breakdown. Okay, so this feature makes Zener diode to be used as voltage regulator. So voltage will be constant and current will go on increasing. Clear? So as a whole for this question, the answer is Zener and avalanche breakdowns. Okay. So here you can see, according to this question, the two different types of breakdown in diodes are Zener and avalanche. Now, logically, as I've told you earlier also, option C also will go correct because the two breakdown names are given in option C also. But specifically, I am saying option A because the two different types of breakdown, this word breakdown is used in the question. So breakdown in diodes are Zener and avalanche. Okay. Then we'll go to the next question. A JFET has three terminals, namely a cathode anode grid, emitter base collector, source gate drain, emitter base on base. So out of this, the three terminals what we have seen for junction FET, that is field effect transistor, are source, drain and gate. So option C will be the right answer here. Source, gate and drain will be the right answer. So option C, you can take it as the three terminals of JFET, that is junction field effect transistor. So here you can see a structure of N-channel JFET. So this is a P-type material which is used in a N-type semiconductor, which is the body. Now this body has two terminals. One is the source. This is the source from where the charge carriers will be flowing. Okay, and this is the drain where the charge carriers will be collected. And the two P-type semiconductors which will be internally joined and taken as a gate terminal. So as you increase the reverse bias on gate, the width of the depletion layer here and the width of the depletion layer here will go on increasing, and the channel, that is the path from source to drain, will go on becoming less, and the current flow from source to drain will go on becoming less. Okay, now in this question, It has been asked that what are the three terminals. So the three terminals of JFET will be source, drain, and gate. So here you can see option C, that is source, gate, and drain will be the right answer. Then we'll go to the next question. A silicon controlled rectifier consists of dashed layers of semiconducting materials. So how many layers of semiconductor materials a silicon controlled rectifier, that is SCR, has? So we have seen the structure of SCR. So in the structure of SCR we had P-type material, N-type material, again we had P-type material, again N-type material. And the first P was taken as a terminal anode, the last N was taken as the terminal cathode, and the in between P, the second P is taken as gate. So anode, cathode, and gate were the three terminals. Now in this question it has been asked that how many semiconducting layers are there? So we have one semiconducting layer here, two here, three here, and four here. So there are four semiconductor layers. So option C will be the right answer. So here you can see the structure of SCR. So this is the first semiconductor layer. So this we can name it as P1. This we can name it as N1, second one. Then this is P2, third one, and this is N2, fourth one. So there are four semiconductor layers, and these four semiconductor layers will have three junctions, junction J1, J2, and J3, and three terminals, anode, cathode, and gate. So in this question, it has been asked how many semiconductor layers. So this is one, this is one, this is two, this is three, and this is 4. So there are 4 semiconductor layers. So C, option C, that is 4, will be the right answer. Then we'll go to the next question. The value of IE, that is emitter current, for the given transistor values of beta is equal to 200 and base current IB is equal to 70 microamperes. So in this case, we have beta, that is the current amplification factor, which will be given as IC upon IB. Okay, so beta is 200, so 200 is equal to IC upon IB is 70 microampere, 70 microampere. So 70 microampere into 200, so IC will be equal to 200 into 70 microamperes. So it is nothing but 2 7 the 14,000 microamperes, which is nothing but IC is equal to 14 milliamperes. Milliamperes. Okay. Now here 14 milliamperes will be your collector current IC. But in the question it has been asked what is emitter current IE. Now we know that emitter current is equal to collector current plus base current. So we can have collector current as 14 milliamperes and base current as 70 microamperes. So this will be nothing but 14.07 milliampere. So emitter current is 14.07 milliamperes. So 70 microamperes we have converted to milliamperes, and that we have added with the collector current 14 milliamperes. So it will come as 14.07 milliamperes. So here option C will be the right answer, that is 14.07 milliamperes. So here you can see the answer, that is the value of emitter current IE if the current gain beta is given as 200 and base current is given as 70 microampere, is 14.07 milliampere. Then we'll go to the next question. The efficiency of a bridge rectifier is how much? Now, when we studied bridge rectifier, we had calculated what was the ripple factor and what was the efficiency of bridge rectifier is 81.2%. So option A will be the right answer here. The efficiency of bridge rectifier is 81.2%. So here you can see option A is the right answer, 81.2%. Then we'll go to the next question. Which of the following IC, that is integrated circuit voltage regulators, is an adjustable voltage regulator? Now IC voltage or regulator will give you a constant output, but that constant output, if you are able to vary with adjusting, then it is called as adjustable voltage regulator. Now what we have studied voltage regulators, and in that adjustable voltage regulator was LM317 IC. So option A is the right answer, that is LM317 IC. So here you can see this is LM317 IC. Now this is shown here. Then the input will be at pin number 3, and pin number 2 will be the output, and pin number 1 will be the adjusting a terminal. So here the output voltage can be adjusted within certain range by varying the uh, pin number 1 input. So output can be varied, but whatever you fix it for, that adjustable voltage will remain constant. Okay. So there, this is called as your adjustable voltage regulator. So it is LM317. So here you can see LM317 is the answer. Then, which of the following IC voltage regulator is an adjustable voltage regulator? So, option A, as I have told you earlier, LM317 is the answer. Then we'll go to the next question. Question number 87. An op-amp operation amplifier can amplify. Options are DC signals only, AC signals only, both AC as well as DC signals, neither DC nor AC signals. Now, one specialty of op-amp operation amplifiers. Now, we have studied 741 op-amp. Now, one specialty was that it can amplify both AC as well as DC signals. So, option C will be the right answer, that it can amplify both AC as well as DC signals. So here, an operation amplifier is a very high gain voltage amplifier. It is used to amplify the signals by increasing its magnitude. Op amps can amplify both DC and AC signals. So here we have shown the symbol of op amp. It has two inputs. One is non-inverting input, one is inverting input. It has two power supplies. One is plus VCC and this is minus VEE. And then it has one output here. So output will be the difference of the two inputs in amplified version. Now, this amplification can be for both DC and AC signals. Then here, option C, as we have told earlier, an op-amp can amplify both AC as well as DC signals. Then we'll go to the next question. A high-pass circuit can also possibly be. Options are an integrator circuit or a differentiator circuit. Option C is either a differentiator or integrator. Option D is modulator. Okay, now here when we studied passive filters or when we studied active filters, now we know that a combination of C and L or C and R will give you the high pass or low pass, or depending upon you are going to connect the a resistor or inductor in series and a capacitor in parallel, or a capacitor in series and inductor in parallel. Okay. Now here, when we studied high pass circuit, high pass filter, now that high pass filter can also act as differentiator circuit. So option B will be the right answer here. Similarly, if it has been low pass circuit, then low pass filter can also act as integrator circuit. But here it has been asked for high pass. So high pass circuit can also be used as, or it can also be act as a differentiator circuit. So option B will be the right answer here, differentiator circuit. So here high pass filter as a differentiator. So at low frequencies, the output of a differentiator is zero, whereas at high frequencies, its output is of some finite value. This is same as for differentiator. Hence, high pass filter is said to be behaved as a differentiator. So in high pass filter or differentiator, we see a capacitor in series with the output, and a resistance or inductance will be in parallel with the output. Okay. So here, if the capacitor is in series and resistance is across, then it is a high pass filtering action or it is a differentiating action. So here you can see option B, high pass circuit can also be a differentiator circuit. So option B is the right answer here. Then we'll go to the next question. A transistor switch operates in. Options are either saturation or cutoff region. Option B is active region. Option C is either active or cutoff region. And option D is either saturation or active region. Now, when we studied these three modes of transistors, now there we had studied that transistor can be operated in active region, transistor can be operated in a cutoff region, transistor can be operated in saturation region. Okay. Now, if you want to use transistor as an amplifier, then it should be operated in active region. But if you want to use transistor as a switch, then you have to use cutoff and saturation both, because in cutoff, the a transistor will be in off position, and in saturation, it will be in on position. So here, according to this, a transistor switch operates in either saturation or cutoff. So option A will be the right answer here. So here you can see the areas of operation for a transistor switch are known as saturation region and the cutoff region. Now here you can see this graph for output characteristics of a transistor in common ammeter configuration. So we have taken the x-axis as VCE, y-axis as IC. We have drawn a load line and we have drawn this output or characteristics. Okay, now in this output or characteristics, the region here will be the active region, and this is used if you want to use the transistor as an amplifier. Okay, but if you want to use transistor as a switch, then you can use this saturation region. This is the saturation region. So here the our transistor will be in on position, and we can use this cutoff region where the transistor will be in off position. So you can use transistor as on and off, that is called as switching. So if you want to use transistor as a switch, then it should be operated in saturation and cutoff regions. So here option A, either saturation or cutoff region will be the right answer. Then we'll go to the next question. In which of the following amplifier classes the active device operates for the whole of the input signal cycle? Class A, Class AB, Class B, and Class C. So when we studied power amplifiers, we have studied these classifications. Now in Class A, the output means the active device operates for the whole of the input cycle. Okay, so here, if the active device operates for the whole of the input cycle, then it is called as Class A type of operation. Okay, so here you can see Class A will be for the complete cycle, that is from 0 to 360 degree. So 0 to 360 degree. Class B will be for half of the cycle, that is from 0 to 180 degree. 0 to 180 degree. Class AB will be in between 180 and 360 degree. It will be in between 180 degree and 360 degree. And class C will be less than 180 degree. Okay. So here these are the classifications what we had seen. Now in the question it has been asked that in which of the following amplifier classes the active device operates for the whole of the input signal cycle. Then for whole of the input signal cycle, if you want the operation of the device, then it is class A operation. So option A will be the right answer. So here you can see class A will be operated for the whole of the cycle. So this whole of the cycle you can see from 0 to 360 degree. Okay, then it is class A operation. If it is 0 to 180 degree, 0 to 180 degree, it is class B. If it is 0, then 180 and 360, it is in between 180 and 360. So it is more than 180, it is more than 180 degree, and it is less than 360 degree. So that will come under class AB operation, and class C is less than 180 degree. So according to this question, what has been asked, if the a complete cycle the our device is going to operate from 0 to 360 degree, then the option is class A. So here option A, class A will be the right answer for this question, where the active device operates for the whole of the input signal cycle. Then we'll go to the next question. The two or conditions essential to satisfy Barkhausen criteria for oscillations are. Now we have studied these are criteria which were necessary for the circuit to go as oscillation. Now here we had an amplifier. So we had an amplifier circuit and a feedback circuit. Okay, feedback circuit. And here we gave the input, and here we got the output of the amplifier. Now this output goes through the feedback back to the input. Okay, now here if the gain of the loop, if the gain of this loop gain, okay, is equal to 1, okay, and if the phase shift, that is 180 degree phase shift, will be provided by the amplifier, and the feedback will provide another 180 degree. So 180 degree plus 180 degree will be 360 degree or 0 degree. If you maintain these two criteria, then this circuit will have a positive feedback, and this will give you oscillations. So these are the two conditions for creating oscillations. To make the amplifier work as an oscillator, we have to have a positive feedback. So loop gain is unity and phase shift is 0 degree or 360 degree. So option A is the right answer. These are the two conditions of Barkhausen criteria. So here We can see the circuit will oscillate when two conditions called Barkhausen's criteria are met. These two conditions are number one, the loop gain must be unity, that is one. And number two, the feedback signal feeding back at the input must be phase shifted by 360 degree, which is the same as 0 degrees. So here, option A, that is loop gain is unity and phase shift is of 360 degree or 0 degree is the right answer. Then we'll go to the next question. Which of the following oscillator type provides extremely stable output frequency? So oscillator is going to give you output, which will be a repetitive waveform. In that repetitive waveform, which oscillator gives you a stable frequency? The frequency F is not going to vary, and that oscillator will be your crystal oscillator. Because in crystal oscillator, you don't have any RLC components. It is not going to deteriorate or attenuate the output, and the frequency will remain constant. It will remain stable. So the stable output frequency is obtained in crystal oscillator. So here, a crystal oscillator gives the most stable oscillation. It is the only not consisting of RLC elements and does not deteriorate over time easily. It provides high stability and precision over a range of frequencies. So here, option C, a crystal oscillator will be the right answer, which is an oscillator which provides extremely stable output frequency. Then we'll go to next question. In ammeter, the moving coil carrying current is called as. Options are data conditioning, data transmission, data presentation, primary sensing. Obviously, the moving coil is going to sense the field, the magnetic field which will be produced. So it is a primary sensing. So option D will be the right answer here. So here, in ammeter, moving coil carrying current is called primary sensing. Then we'll go to the next question. The degree of closeness with which the instrument reading approaches the true value of the quantity to be measured is called as. If your reading is approaching the true value, then you are becoming more accurate. Okay. So this statement, that is the degree of closeness with which the instrument reading approaches the true value, of the quantity to be measured, then this is you are going towards more accuracy. So here option C will be the right answer. This statement gives you the definition of accuracy. So here you can see the degree of closeness with which the instrument reading approaches the true value of the quantity to be measured is called accuracy. Then we'll go to the next question. In electrostatic type of indicating instruments, so options are scale is non-uniform and size is large. Option B is most useful for low voltage measurements. Option C is can be used only for DC measurements. Option D is it is based on the principle that there exists a force between plates with same charges. Now, if you see the disadvantages of electrostatic type instruments, then in that disadvantage, there is a option that the scale is non-uniform and the size is large. So these are the disadvantages of electrostatic type indicating instrument. So here for this question, option A will be the right answer. That is, its scale will be non-uniform and size is large. Okay, so in electrostatic type of indicating instruments, the scale is non-uniform and size is large. So here you can see the disadvantages what we had studied for electrostatic type instruments. The number one disadvantage was the non-uniform scale is used in the instrument. Number two, the force of very small magnitude involves in the instrument. Number three, the instrument is quite costly as compared to other instruments. Number four, the size of the instrument is also very large. So here the first disadvantage and the fourth disadvantage is given in the option, and that will be the correct answer for this question. So here in electrostatic type of indicating instruments, the scale is non-uniform and size is large. Then we'll go to the next question. In frequency selective wave analyzer, the high Q, that is a quality factor, the high Q filter is consists of. So the filter which is having high Q consists of what? Now from these options, it consists of RC resonant sections. RC, that is resistance, capacitor, resonant sections, and filter amplifiers. So it is option C which is the correct one. In frequency selective wave analyzer, the high Q filter consists of RC resonant sections and filter amplifier. So here the wave analyzer used for analyzing the signals are audio frequency range is called as frequency selective wave analyzer. High Q filter. It is used to select the desired frequency and reject unwanted frequencies. It consists of two RC sections and two filter amplifiers, and all these are cascaded with each other. So it is RC sections and filter amplifiers. So here you can see option C, RC resonant section and filter amplifier is the right answer. Then we'll go next question. The passive transducer. The options are LVDT, linear variable differential transformer. Option B is photovoltaic. Option C is electromagnetic. Option D is thermoelectric. So out of this, the passive transducer is LVDT. That is option A is the right answer. That is linear variable differential transformer. So here LVDT, linear variable differential or transformer, is a most useful passive transducer. The main function of a LVDT is to produce an electrical signal equivalent to the movement, that is generally rectangular, of an object. LVDT is nothing but an electrical transformer with a movable core. So here you can see the diagram. This is the primary winding and we have two secondary windings. So this is the primary winding and we have two secondary windings here, and whatever excitation you give at the input, the output you will get one voltage across the first winding S1 secondary. So this is V1, what you get the voltage across the secondary winding first part, and across the secondary winding second part we get the voltage as V2, and the output will be V1 minus V2. Now this output is going to vary according to the movement of this core, whatever you are having here. This movable core, it will go up and down. So as you vary this, the output voltage is going to vary. That means movement displacement is converted into electrical signal, and this is a passive transducer. So here you can see the passive transducer is LVDT, that is linear variable differential transformer. Then we'll go to next question. Frictional errors in digital instrument are due to what? High input impedance, auto ranging, no moving parts, hence no errors. Reading speed is very high. In a digital instrument, there are no moving parts and therefore there are no frictional errors. So option C will be the right answer. No moving parts, hence no errors. So here you can see option C, no moving parts, hence no errors, is the right answer for this question. Then we'll go to the next question. In digital frequency meter, input signal is converted to square wave with fast rise and fall times using which circuit? Options are amplifier, digital readout, start stop gate, Smith trigger. It is the Smith trigger circuit which will convert the input signal into a square wave. So option D will be the right answer, Smith trigger. So option D, the Smith trigger, is the correct answer. Then we'll go to the next question, question number 100. The firing angle for R triggering circuit. So when we studied a triggering circuit for SCRs, we studied R triggering and we also studied RC triggering. So R triggering was able to give you the triggering angle option from 0 to 90 degree, and RC gave you the option from 0 to 180 degree. Okay, so R triggering will give you the option from 0 to 90 degrees. So here option B will be the right answer. The firing angle for R triggering circuit is 0 to 90 degree. So here you can see in this a triggering angle is limited to 90 degrees only because the applied voltage is maximum at 90 degrees. So the gate current has to reach minimum gate current value somewhere between 0 to 90 degrees. So here you can see this is the SCR shown here. This is the SCR shown here, and this is the signal which is going to trigger the SCR, and it is controlled by the resistance R. Now here you can see that our triggering angle can be varied between 0 to 90 degrees. So this is the variation only from 0 to 90 degree. Even here it is from 0 to 90 degree. Okay. So here option B will be the right answer. The firing angle for R triggering circuit is 0 to 90 degrees. So option B is the right answer here. Okay. Thank you, students.